Swayam Prabha. Digital India. Educated India.
So, last class I have discussed how you can calculate the immediate settlement of clayey soil. Now, today first I will discuss about how you will calculate the consolidation settlement of the clayey soil, and then I will discuss about the methods by which you can determine the settlement of the granular soil. Now, so this is the different procedure that I have discussed, that this first and second are for the clay and rest of the 5 procedures are for the determination of settlement of sandy soil. So, I have discussed the immediate settlement for clay. Now, the consolidation settlement. So, this is the equation by which I can calculate the consolidation settlement. So, this is the equation, you know, this is very famous equation to calculate the consolidation settlement, and you have done the derivation, or you know how this settlement is coming. So, that is these are your soil mechanics part. So, these will those things will not be discussed here, because we will directly use this equation, but I will explain what are the different terms. So, your Cc is the compression index and E E0 is the initial void ratio. So, compression index, you know how you will calculate. So, if you have E log P curve, then the straight portion slope will give you the Cc. Okay, so these are the soil mechanics part. So, you should know these things, because I had the okay. So, now Cc you will get from the odometer test, odometer test. So, that means this test you will get the Cc value and E0 value, and then H is the thickness of the your soil layer, and P0 is the effective overburden pressure. Actually, this is P0 dash, this is effective overburden pressure. So, initial effective overburden pressure and before applying the load. For example, that if you, this is the foundation, okay, and this is the ground surface, and you have different layer. This is layer 1, this is layer 2, this is layer 3, and so on. So, remember that for bearing capacity equation, the thickness of the layer below the foundation base up to equal to width of the foundation is considered. So, that means for bearing capacity calculation, influence zone is taken as B. Okay. So, that means for bearing capacity equation calculation, the influence zone is taken as B. From where? From base of the foundation. Okay. So, for bearing capacity calculation, the influence zone is taken as B from the base of the foundation, but for the settlement calculation, the influence zone is equal to twice B, where B is the width of the foundation and said dF is the depth of the foundation. Clear? So, this is do not forget this, for the bearing capacity calculation we consider influence zone as a B from the base of the foundation. For settlement calculation we consider influence zone as a twice B from the base of the foundation. So, both the cases is base of the foundation. So, and another thing you should remember, suppose within your influence zone there is a rigid strata. Okay. Suppose this third layer is a rigid strata, okay, and your influence zone is going to third layer. This twice B for bearing for settlement calculation, the influence zone is going to third layer. So, then you do not consider the third layer contribution, because as it is a very rigid strata. So, it is expected there will be no settlement or very significant amount sorry, very insignificant amount of settlement or negligible amount of settlement. So, in such case your influence zone will be up to the rigid strata, that means from base of the footing to the rigid strata, but even if that thickness may be less than twice B, that thickness may be say 1.5 B, because that 0.5 B portion is within the rigid zone. So, that means in that case you do not consider the 0.5 B zone, only consider that 1.5 B zone or 1.25 or 1.75, whatever it is, because if it is a rigid strata is within your influence zone, then do not consider the contribution of that rigid strata, your contribution of the strata which is not rigid within the influence zone, that you have to consider only. Clear? And suppose if you within the twice B there is no rigid strata, then you consider up to twice B, and that may be within your third layer also, that may be fourth layer, any layer. Okay. So, this you just remember that. So, now I am just calculating that how you calculate the P0 dash. Okay. So, the for P0 dash, suppose this is up to this is your influence zone. Okay. So, up to this is your influence zone, and I am this is the thickness of the first layer, say H1, this is the thickness of the second layer H2, but I am not considering the thickness of the total third layer, I am considering the thickness of the up to the influence zone. Now, if the third layer is rigid strata, but H3 is within the third layer, then you have to consider up to this H2. Okay, remember that. So, this is the third layer. So, what we will do? We will consider one particular point, the middle of the each layer below the foundation. Okay, so middle of the each layer. So, this is B point, this is C point. So, that means this A layer is the middle of this, A point is the middle of this thickness. Okay. So, A point is the middle of this thickness. Similarly, B point is the middle of this, here I can write this is H2 by 2, and if this is a small h, then this value is small h by 2, and this is will be H3 divided by 2. So, that means middle of each layer. Now, the question is only one point, why we are only considering one point. So, no, if you consider more points, so your accuracy level will increase definitely, but you have to check whether that accuracy level is significantly increasing or not. So, most of the cases if I take one point, then that is okay, but if the layer thickness is very high, then you can take more points also. In such case, you divide the even the a particular layer into number of zones or number of layers. So, for example, you divide the layer 2 into say 3 more layers, and then take the point the middle of that 3 layers. Then you do the calculation, the same process that I will show. Okay. So, but in most of the my example problems, I will take only one point at the middle of each layer, but if you want, you can take more points also. In such case, your accuracy level may increase, but if it is not significantly, then one point is sufficient. Okay. So, that means now the P0 dash is the effective overburden stress at each point. So, each point you have to calculate the effective overburden pressure. For example, A point, the effective overburden pressure, I am considering all the cases unit weight is same. But remember that suppose if you have different unit weight and different location, and so because I have already discussed that thing during my layered soil bearing capacity calculation. So, if you have a different unit weight at different location, you have to calculate effective overburden pressure accordingly. So, you should know where you have to use the gamma bulk. That means, if the zone is above the water table, then you have to consider gamma bulk. If the zone is below the water table, then you have to consider gamma sub. Okay. But here I am considering all the gamma are the same, but actually it will not be same in the field. So, you have different gamma, even different layer will have different gammas, even in the layer also the water table may present. So, we have to take care of all those things. So, P0 will be in this case that gamma df into gamma, or I should write gamma 1 because this is the top layer, the second layer, then plus h by 2 gamma 1. So, P0 at A. So, this way I can calculate P0, but remember that this is effective, it is not total. Then P0 dash at B will be equal to H1 gamma 1 plus H2 by 2 gamma 2 and so on. Okay, so, this is the H1 into gamma 1 plus H2 by 2 gamma 2, okay, and this is the P0 for at A equal to A. So, this way I can calculate effective overburden pressure. But now there is an important term which is del P, that vertical stress at the center due to application of load. So, how you can calculate that? Okay, so, there are number of way you can calculate that. You can use Brusenic method to determine the stress for a particular point. So, but during this design I will use the simplified method, which is 2:1 distribution. So, what is that? Suppose if you have a foundation, this is the foundation. So, I want to calculate that delta P at B point. So, I will distribute, assuming that the stress is distributing like this, which is a 2:1 distribution. Okay? 2:1 distribution. So, in such case, if this is a 2:1 distribution, suppose if you have a footing dimension of this is 2:1 distribution. If you have a footing dimension of B cross L, okay, and you have a Q is acting as the base of the footing. Okay, so, that means that this stress which is acting as base of the footing, that is equal to Q. So, total load which is acting at the footing, that will be equal to small q into B into L. So, this is the total load, net load acting on the foundation base. Okay. Now, when this load will distribute at 2:1 distribution pattern, then this loading area will increase as the depth increases. So, at point B and at the base of the foundation, the loading area will not be same. So, loading area will be increased. So, that is why your stress at that point B will decrease as compared to the surface of the base of the foundation. So, that means as your depth increases, the stresses due to external loading will decrease. So, del P is the additional stress or the increment of stress due to the application of external load. So, now how I can calculate the del P? Del P at point B, say. So, I know total load, now my area is been increased. So, now what will be that area? So, that area will be B plus this is small h plus H2 by 2, because your depth of the point from the base of the foundation is h, small h plus capital H 2 by 2. Okay. So, now as it is 1:2 distribution. So, now if this is your say any depth z, so this will be definitely z by 2, okay. And this is also this side also, if this is any depth z, this will be z by 2 because it is 1:2 distribution. Okay. So, that means if this is z, this one is z, this will be z by 2. If again this one this is z by 2. So, your total area will be increase what? Z by 2 plus b plus z by 2. So, this will be simple b plus z. That means b plus the distance from the base of the foundation to that point, and that distance is z, but in this particular case it is small h plus capital H 2 by 2. So, that I have written small h plus capital H 2 by 2. Similarly, this is in the width direction, there will be another one in the length direction. So, this will be L plus small h plus capital H 2 by 2. Okay. So, this way you can calculate the del p. So, this is the simplest way, and I will use this method for this particular case when you solve the example problem or design problem. So, that means I have discussed how you calculate the effective overburden pressure, how you calculate the del p, then compression index you will get from the lab test, E0 value also you will get from the lab test, and then MB. So, if you use this thing, this first equation, then this is sufficient. If you use the, because this is H0 and H both are same, the thickness of the each layer. So, you can write this is also H0, does not matter. So, this will be the sum, and if you use the second thing, then you need the coefficient of volume compressibility. That also you have to determine by consolidation test. So, which one you will use it depends on the availability of your design properties or design parameters. If you have the CC and E0, then it is better to use the first one. If you have MB, then you can go for the second one. So, that means each layer you have to calculate the settlement for each layer. Then to get the total consolidation settlement, you have to add them. So, that is why it is summation. So, first you calculate the settlement contribution for each layer, okay, and then we will add them and we will get the settlement contribution for all the layers, that will be the total consolidation settlement. So, again here also we have to apply 3 corrections. So, one is depth correction factor or depth correction, as I mentioned, these are again all valid for the surface footing. So, if we have depth of foundation, you have to apply the corrections, and the same way we can calculate the depth factor by using Fox depth factor correction chart. So, that I have discussed, and then we have to go for the rigidity correction also. So, these all equations are valid for the flexible type of foundation. If we are using for the rigid foundation, you can use them, but we have to apply rigidity correction, and that value here also 0.8. So, rigidity correction factor will be 0.8. Then another corrections we have to apply, which was not applied in the immediate settlement, that is pore water pressure correction. What is that? Because this theory is called the 1D consolidation theory. That means, it is assumed that this consolidation is going only in the vertical direction, but actual field, when we apply a load or stress on a particular soil, your water can move any direction in 3 directions. Okay. But here it is assumed that in this equation it is assumed that it is moving only the vertical direction. So, it is only one direction, but actually it is pore pressure is developed, it is what is moving in the 3 directions. So, that is why you have to apply the another correction, that is called pore water pressure correction. So, that pore water pressure correction, that means actual consolidation is the 3D consolidation, but here the consolidation equation that we are using, that is 1D consolidation equation. So, this is the correction. So, to get the CD correction, you have to apply a lambda, which is a correction factor. So, that we will use with multiply with the uncorrected settlement value. So, now we can use this chart, which is given in IS code. So, this chart you can see for this is a pore pressure parameter A, and you know that the pore pressure parameter A and B, two parameters are there. So, it is in terms of pore pressure parameter, pore pressure coefficient A. So, that means here if it is A is 1 to 1.2, then it is very sensitive clay, then 0.5 to 1 is normally consolidated clay, and 0 to 4.5 is over consolidated clay. I have discussed what is normally consolidated clay, what is over consolidated clay, and this is values of the curve HT by B. HT is the thickness of the layer below the foundation. So, that means the thickness of the total influence zone I am talking about below the foundation is called HT, and B is the width of the foundation. Dotted line is for your strip footing, dotted line is for strip footing, and the farm line is for the circular footing, and this is 0.25, 0.5, 1 and 4. So, this is this one 0.25, then dotted this is 0.5, this one 1 and this dotted 4. Similarly, this farm 0.25, this farm this is 0.5, this farm 1 and this is 4. Okay. So, this the chart, if you have the A value, then you corresponding to that A value, whether it is a circular footing or strip footing, and in between that, if it is in between that, then you can linearly interpolate the value. Suppose you have a rectangular footing, then first you calculate circular, or which for square also you can use the circular footing part. So, which is same more or less. So, for circular or square you use the farm 1, and strip you use the dotted one, and if it is rectangular footing, then you use you can interpolate the values. So, that means here if you have the H by B ratio, you know that, and if you have the A value, then you can calculate the coefficient, that is lambda, by using this chart. Okay. But sometimes these A values are not available. So, if you do not have the A value, then you can use these ranges also. These ranges also you can use to get the lambda value. So, for very sensitive clay, it is 1 to 1.5, normally consolidated clay this is 0.7 to 1, over consolidated clay 0.5 to 0.75, and heavy over consolidated clay 0.3 to 0.5. So, if you have the A value, then you can use this chart. If you do not have the A value, then you can use the value which is given from this range, because this is a range, but here if you have the A value, then actual value you can, or factor you can get from this chart, but here you can get a range, but if you do not have the A value, you can use these ranges. Okay. So, now as I mentioned, this is the rigidity factor and depth factor. So, that means you have to use these corrections factors, and as I mentioned, this rigidity factor is 0.8. Now, next one I will discuss about the settlement calculation by using the settlement calculation for the granular soil by using the plate load test, then the SPT value, then the SCPT value, then the influence chart method or semi empirical method. So, in the plate load test is done in the field. Okay. So, this is the field test for the shallow foundation, by which not only the settlement, we will get the bearing capacity of the foundation also. So, we will get the bearing capacity as well as the settlement by using plate load test. But the advantage of this test is that there is the most of the field test what we either calculate or determine the soil parameters directly or indirectly. Then we use those parameters in our bearing capacity equation, and then we will get the bearing capacity. But in the field plate tested directly in the field, we will get the what is the bearing capacity without using any parameters, all these things, or direct value we will get that from the field. So, that is the advantages. So, this is this is a short term test. So, it is not suitable for cohesive soil generally. So, that means although we will give we have the equations or the correlations available for cohesive soil also, but it is recommended you use this test, any field test, for cohesionless soil, because that will give better result for cohesionless soil, because these tests are short term test, and your cohesionless soil settlement is short term, because immediate type of settlement. So, that is why you use these tests for cohesionless soil, and with cohesive soil settlement is a long term settlement. So, that is why you use it is not recommended to use these test data directly for the cohesive soil. You can use them, but you have to cross check it with other methods also in case of cohesive soil. So, plate load test, what the plate load test? So, it is done, it should done at the base of the foundation. That means, the depth of the plate should be equal to the depth of the foundation. So, that means, suppose we have a test pit, and there so this is the test pit. So, in depth we have to conduct the plate load test, and depth should be equal to the depth of the foundation. Okay. So, then we will place this stack plate, because these will help us to give the load on the plate. So, this is your a hydraulic jack, and then through this hydraulic jack we will provide or apply the pressure, and we will use the reaction frame also. So, this is the reaction frame that we will use. So, basically we will apply this hydraulic jack, and we will these loads will be applied, or pressure will be applied through this reaction frame on the plate. So, that means, basically we are applying the pressure on the plate, and then we are measuring the settlement of this plate. That means, the ultimate output will be pressure versus settlement. So, we are applying the pressure, and we are measuring the settlement. So, and we are placing the plate at the base of the foundation, and then we are applying the pressure. So, generally this width of this pit, the minimum width should be the 5 times of the width of the plate. Okay. And ideally this should be the DF, but if it is not, then again we have to apply the correction. Okay. So, now as I mentioned, we have to use the dial gauge. So, we have to use the dial gauge to measure the settlement of the plate. Okay. And then this is the pressure gauge, which will give us the pressure reading, and this is the dial gauge, which will give us the settlement reading. Okay. So, this is dial gauge. Okay, this is the dial gauge, and this is the pressure gauge. Okay, so this is dial gauge, this is pressure gauge, this is reaction frame, and this one is the hydraulic jack. Okay, and this is the plates. So, we will get the settlement and or the pressure corresponding settlement. Suppose this is the pressure and the settlement. So, we will get this type of curve. Okay. So, that means here we will get the curve, and now from using this curve we will from this plate we will get the bearing capacity of the foundation as well as the settlement of the foundation. So, that I will discuss. So, ultimately we will get the pressure versus settlement curve, and you should know some tips and the procedure for this particular test. So, we can use the plate of rectangular plate or circular plate of size 30 centimeter, 45, 60 and 75. So, why 30 and 75 are the two limits? So, because it is observed that if the plate size is less than 30 centimeters, so your results that you are getting are not reliable, so are not good. So, that is why do not use any plate which is less than 30 centimeter. And 75 centimeter also it is observed that after 75 centimeter the difference of or the effect of plate size is not significant, okay? It is negligible. So, that is why you use 30 to 75 millimeter centimeter plates, because after 75 no such size effect is there. So, when you do the plate test, before you place the plate on the foundation bed or the soil, you place a 5 millimeter thick sand pad, then you place the plate. Okay. The smaller sizes plates are used for dense or stiff soil, and the larger size is used for the loose and the soft soil. So, if there is a water within your test pit, you just pump the water and remove the water from the pit, and so these loads are giving the reaction frame. So, that I have discussed, and before we apply the actual load, a sitting load of 70 gram per centimeter square or 0.07 kg per centimeter square is first applied on the plate, and then it is released after some time. Why it is applied? Because it will make sure there is a perfect contact between the soil and the plate. So, it will act as a sitting load. So, then load is applied on 1/5 the estimated shape load up to the failure, or at least 25 millimeter settlement, whichever is earlier. So, these are the procedures. So, in the next class I will complete this part. Okay. So, because there are some more tips are there. So, you should know that those tips, and again I have discussed the advantage of the plate load test, but there are some limitations or disadvantages also. So, I will discuss those things in the next class. Thank you.